I do have my timer, but I do have my timer, but if you see that I'm ignoring it, don't hesitate to. Okay.
Okay, so I assume sound is still fine. Can you hear it?
So hello everyone. Can people from all? Okay. Oh, we will start in 1 minute. Start. Okay. Thank you, Mathieu. Thank you. Thanks to all the organizer of this open data workshop, local organizer, and people, Agatha, for the GUOSC. I'm Francesco Di Ranzo. I'm the coordinator of Virgo DetChar, which is going to be the subject of this presentation. So in one of the last slides of Marion, you've seen a flow chart which places DetChar right after what is instrument science and before observational science. So sort of linking what are searches and parameter estimation. And today in this presentation, I'm going to provide a little bit more details on that and hopefully convincing you on the importance, likely for everybody, to take an eye on data quality and have some basic knowledge about detector characterization. Okay. Okay. Check now. Okay, it does. Okay, the pointer works. Okay, so these slides with the is divided in 3 parts. On the right-hand side, we have instrument science, so schematic layout of the optical design of a detector, the design of super attenuators, which are important for an aspect that I will briefly comment later on, and a map of some environmental sensor. This is on the left. On the right, sorry, is on the right. On the left-hand side, we have astrophysical sources, the main 4 sources that Viola introduced yesterday. And the most important thing of these slides are the 2 arrows, one pointing to left and one pointing to right, to represent a sort of cyclic exchange of information between the 2 words, observational science on the left-hand side and instrument science. In the middle is where detector characterization stands. So briefly, detector characterization is about monitoring the detector, the states of the detector, its subsystems, and their physical environments. We want to characterize the data collected by our detectors, investigating noise sources, and hopefully mitigating them to have more sensitive detectors. Also, we want to inform searches and the parameter estimation about the quality of the data to say them like, pay attention, this data is not super clean. You can be misled to consider this excess energy as a astrophysical signal, while it is not. So overall, detector characterization is about to ensure that the data that we collect with our detector is usable, reliable, from the example that I just made, and most of all, our detectors are understood. So this map shows where detector characterization stands within what is called detector operations. Again, a 3-part slide with on the right-hand side the detectors from top: Hanford, Livingston, Hanford, Virgo, Livingston, and Kagra. I mixed the 2 with respect to alphabetical order. On the left-hand side, we have the publications of the LIGO, Virgo, and Kagra collaboration. And equally important, we have the open data, which of course is important, not just because it is the subject of this workshop, but because it allows the entire scientific community to follow and reproduce our scientific results. And in the middle of this page, we have, I don't know if people in the auditorium can read it, probably it can be seen a little bit better from online. So in the middle of this map, we have detector characterization. So this map has arrows representing the data flow from the detector, so the instrument science part, two searches on top here, on top at the center of the map. And on the right, we have parameter estimation and all the inference that we can make on the data that we collect. So this is briefly what is detectorization about and where it fits in the collaboration activities. Let's have a quick recap on the detector working principle. I'm basically taking over from the presentation of Viola, adding a little bit more detail on the noise that we actually detect. So at the top left of the page, we have a simplified scheme of a Michelson interferometer or gravitational wave detector. As Viola told, we have mirrors that act as test masses. And the transit of a gravitational wave, with amplitude h, is converted into a variation of the proper distance between the mirror. Delta L is proportional to h times L, the distance between the two mirrors. This can be detected with Michelson interferometer configuration as a power, a difference in power reaching the output, the detection photodiode of the detector. This power is proportional to the input power, the amplitude of the wave, the distance between test masses, roughly speaking, the length of the detector arms, divided by the wavelength of the laser light that we use. So already with this simple scheme, we find some limitations. So we use light as a sort of ruler, but light we know is quantized. So the first and probably one of the most important kind of noise that we encounter is quantum noise. Quantum noise is due to the fact that light is packed into photons, okay? So what arrives at the detection photodiode is actually a slightly variable number of photons. It is described by a Poisson distribution. So we have a sort of error, uncertainty in the counting of photons arriving to the detection photodiode. This is called shot noise. And this is described by the first term in this equation. S of h, the power spectral density of the noise. You already know what is the power spectral density from the presentation by Kentan. This is described by this first term. So inversely proportional to the power, the injected power to the detector. This is not the only issue from quantum mechanics. We have also a position measurement error, which is called radiation pressure noise. Photons, in addition of being quantized, as a momentum. So when they hit the test masses, the mirror, they exert a force. But since the number of photons is variable, also the force is variable. So masses are like shaking, okay? This poses a limitation described by this second term. It scales like proportionally to the power. The larger the power hitting the mirrors, the larger the shaking of the mirror. And it scales like f to the -4. Okay, so it's kind of steep in these plots. There are various ways to beat this standard quantum limit, this quantum mechanical limitation of the detectors. I just list a few of them and briefly comment them. First way is to use Fabry-Perot arm cavities. That is, I recycle the light in the arms, making it bunch back and forth about 100 times. This has the effect to increasing the effective length of the arms by a factor 100. So not 3 or 4 kilometers, mostly 400 kilometers. Then we can do a similar technique at the input of the detector. We place here, right after the laser, a power recycling mirror, which reject back the light trying to exit from what is called the symmetric port of the detector. So from the beam splitter to the laser. This has the net effect to increasing the circulating power inside the detector. So instead of POI, we get a factor POI times again G PR, power recycling. Next trick is to introduce a signal recycling. The reason is that the longer our detector arms, the less sensitive we are to high frequency wave, in the sense that our detectors act more or less as a low pass filter, okay? We want to slightly reshape the sensitivity band of our detectors. So we introduce this mirror here called signal recycling mirror or signal extraction mirror to slightly broaden the band, the sensitivity band of other detectors towards higher frequency. Last trick to really kind of beat the quantum mechanical limitation is to inject squeezed light at the output of the detector. There is the way we did it in O3, which has practically the effect of having a larger power, an effect similar of having a larger circulating power inside the detector, so improving the sensitivity at high frequency, but without really injecting more power. We can do an even finer trick. This is what we have been trying to work on during O4 with little success, and which we will implement for sure in IR1, which is to use frequency-dependent squeezing. That is, we want to have like less power at low frequency, where we are limited by radiation pressure noise, and more power at high frequency, where we are limited by shot noise. This is called frequency-dependent squeezing, very refined technique. So in this plot, we have a black curve representing our sensitivity. It is a model, the total noise, the total sensitivity of our detector as a model. And the various curve represent the noise budget. So the individual contributions that summed give the black curve, the sensitivity of the detector. And in this plot, well, for now, I have only introduced the purple curve, which are quantum fluctuation, so quantum noise in its form of shot noise and radiation pressure noise. I briefly mentioned other 3 or 4 main fundamental noise sources, which are seismic noise, detectors on ground, so now LISA, Livingston, Hanford, Ergo, etc., are subject to the microseism that we have on ground. So on ground, the ground is shaking by about 1 micrometer per second, with a spectrum going as a power law, f to the minus alpha, with alpha between 2 and 4, typically 4 above 1 Hz. How we can beat this noise? Well, using super attenuators, chain of pendula, like 6 stages of attenuation, reducing every stage, it reduces as f to the second. So with 6 stages of attenuation, we have f to the 12 plus the spectral index of the microseismic noise, which is sufficient to have at high frequency, so above 1 Hz, sensitive detector, so not to be limited by short seismic noise. Another form of noise which is more subtle is gravity gradient noise. So fluctuation in the density around the detector, in the ground, but also in the atmosphere, interact directly with test masses. This is a problem. We cannot insulate gravity. Everything that gravitates, we cannot shield gravity. We know that. And the way we have found to beat gravity gradient noise is to use an array of Newtonian sensor, array of gravity sensor, and subtract in low latency the effect of varying density around the detector. This is implemented in one of the main buildings of Virgo. Not yet operational, as we turned out that we are not yet limited by gravity gradient noise, as I will show in a few slides. Here I'm showing how it scales with the frequency. So same scaling as the seismic noise divided by f to the second. Suspensions, pendulum attenuations have no effect on gravity gradient noise. I told you, we cannot shield gravity. Next kind of noise that it's our detector is thermal noise. We have thermal noise in the wires that suspends our mirror, but also in the thin layer of coating of our mirrors. That is in the what makes our pieces of glasses actual mirrors. Okay. So thermal noise from the suspension, the blue curve, scales like f to the fifth. So it's kind of deep in this plot of the sensitivity curve and the noise budget. Cotin-Brownian noise is a little bit less steep, well, much less steep, f to the -1. And as you can tell from the plot, the red curve, it's the main limitation that we have. We will eventually have in the bucket, in the most sensitive area region of our detector. So, well, more or less, we have quantum noise and this Cotin-Brownian noise. This is what happens in an ideal world. Our detectors are much more complex, and this beast here is an actual noise budget where the black curve is what we measure. And if you squeeze your eyes, you can see that measure PNS 59 megaparsecs. The green curve, the thick green curve, is what we understand of our noise. And again, from the legend, you see 66 megaparsecs. There are 7 megaparsecs that we cannot understand why they are missing from our noise budget. This is from O3. This is from the detector characterization, Virgo detector characterization paper from O3. I'm not going to describe all of this group, just to mention that things are much more complex than what we actually understand. And I quantify how much we don't understand as 7 megaparsecs, okay? Which is the distance between these two curves. I put here this slide, this picture, just to tell that things are much more complex, but also to show another thing. So this smoothed curve, this blue curve, is called the noise baseline, which represents sort of upper bound to our sensitivity. It is, if we are able to remove all the fuzzy thing on top of it, we could see as much as this, okay, at this distance. Fine. On top of it, this purple curve is called spectral noise. Spectral noise is an unwanted feature in our data, which soon I will call in a specific way. And it's described by various terms like spectral lines, if they are very thin, bumps, shoulders, depending on the shape of the spectral feature. And now I give a sort of definition, or to be precise, I give 3 equivalent definitions. I call data quality issue, probably one of the most important terms that I put in these slides. I call data quality issue every noise feature that reduce the ideal performance of our analysis. And as you remember, I referred to this blue curve as sort of idealized sensitivity, baseline sensitivity. So an equivalent definition of data quality issue is everything not represented by this blue curve. Again, third definition, operational, somewhat, and related, strictly related to the presentation by Kentan. I call noise issue, data quality issue everything, the part of the noise that is not stationary and not Gaussian. Spectral lines are, and also most of the spectral features are usually non-Gaussian, which is an issue for most of the analysis because, as probably Tito will comment in his slides, we more or less always assume that the data is described by stationary and Gaussian process. Also, Viola commented on that. If it is not, well, this is an issue, a data quality issue. Data quality issue. Let's start from transient noise. So transient noise is typically divided into glitches, which are fast transient. The most famous one is this big glitch, the correspondence of the BNS signal of August 2017 on top of Livingston data. They have various shapes in this kind of spectrograms. And there is this project called Gravity Spy, which tries to relate the shape of this excess noise in the spectrogram to potential sources. So this citizen science project, Gravity Spy, asks people to classify excess noise based on their shape, trying to find a connection with their sources. Some notable glitches obscuring BNS signal is this one, and also this one from GWTC, is GWTC2 probably, from O3 in any case. We have also slow no stationary noise, as you can see from these few hours of BNS range from the Livingston detector. There are varying by something like 5, 10 megaparsec. Is a varying BNS range. This poses a problem because for doing parameter estimation, but also detection, we want to understand the noise of the detector. But if the noise varies over tens of minutes, it's a little bit difficult to tell the search which sensitivity curve to use to estimate what stands on top of it, what is not the stationary noise. This is called slow no stationary noise, another complication. Effects of no stationary noise, but in particular on glitches. So I should have commented here. Glitches impact searches because they can mimic a signal. So if we have a wide enough parameter space, we can fit a glitch with sort of high mass CBC signal, high mass hyperprocessing by CBC signal. So this will lead to a false detection, but also it can cover a true signal, leading to a missed detection, which is a problem. I'm showing here other biases of the glitches that they introduce on parameter estimation. Here I'm reporting two parameters, the chirp mass and the distance. And I'm showing here how these quantities gets biased. So horizontal shift with respect to 0 due to the presence of glitches, and also how the posterior distribution of these parameters gets bigger from the presence of glitches. Sky localization. So in the top plot, there is a small cross slightly off the center, while the red region is where we are able to reconstruct our signal, and there is a bias due to the presence of a glitch. If we remove the glitch in the plot on the bottom, we recover the right position of the source. So glitches bias parameters like mass, distance, and sky localization. Of course, you have also effect on other parameters like the estimate of the Hubble constant. I'm not commenting in detail this thing, I just refer to the article, and also tests of general relativity. The parameters describing deviations from GR get biased from the presence of glitches. So these justify the term data quality issue. How we detect no stationary noise and no stationary non-Gaussian noise. So one direct way is to observe the variations of the power spectral density of the noise on source of source and around the time of possible detection. If there are variations of that, we have tests, statistical tests that say, oh, look, our noise has varied, so the data is not stationary. This could have consequence, pay attention. Another way more direct is directly on the signal. So if we identify a signal within some waveform, we subtract the model for this signal and we inspect the residual, which is the plot at the bottom. This plot should be as clean as possible. This should be compatible with stationary and Gaussian noise, white noise, once we have whitened it. If there is a residual, well, either our model was not perfect or there was other excess of energy on top of our signal, likely meaning that we had a glitch next to our signal. This could have biased our estimate. Other ways to test non-stationarity are what is called Raleigh tests, which investigates is a consistency test for the hypothesis of Gaussianity, or on the bottom we have a test investigating stationarity, again studying how the PSD varies over time. These are all tests that you can done simply using the strain signal. In practice, in LIGO, Bird, and Kagra, we use many more tests, which involves also auxiliary channels. But unfortunately, they are not available on the GWASC, all the auxiliary channels that we use for investigating noise. So I'm not going to comment that now. I will refer to the two papers describing it. Spectral noise. Spectral noise is probably clearer to understand if we have like a continuous source at sort of position, but if in that position in the spectrum we have a bump, a structure, some excess of noise with respect to the ideal noise baseline, we are basically blind due to that spectral noise line or structure, shoulder, bump, whatever. Okay, so it is an issue for continuous wave searches. It is an issue also for stochastic searches, because also stochastic searches, for the most, they use the hypothesis of Gaussianity of the data, but spectral lines are not Gaussian. Simple reason for them, the central limit theorem, which somewhat justified the hypothesis of Gaussianity, is not true for them. So we want to eliminate spectral lines from the analysis. How we do that? We use data quality betas, and you can find on the GWASC a substantial amount of betas. For time domain betas, we divide them in various categories, Cat1, Cat2, and also Cat3, although we are kind of discontinuing them in 04. So this is why it is in gray. So Cat1 beta stands for don't look at the data. The data is corrupted irreversibly, so don't put this segment into your analysis. And indeed, you will find some not zeroed, some nonce in your data if you look at open data in the presence of the Cat1s. Cat2 is more conservative. We know that there is a coupling, a noise coupling between the strain and another channel that witness some excess energy. So what you see in the strain is an excess energy of non-astrophysical origin or environmental or instrumental origin. So you better discard it, although maybe for some frequencies can be clear. I mean, it's up to you to decide. And typically Cat2 are search specific. So we have Cat2 for bar searches, Cat2 for CBC searches, etc. Similarly, for lines, we have frequency domain betas represented by spectral line catalog. So a catalog of frequencies, frequency with their width, their amplitude, describing, okay, at this frequency, we have known spectral noise originating from some resonance of the apparatus from some reason. So you better avoid it in your analysis for the reason that I just said. What if noise is unavoidable, meaning that we have a detection candidate, but there is excess noise? If you look at the plot on the two plots on the left, you will notice an orange curve. This is the waveform of the putative CBC signal. But at the bottom, we have this sort of set of bumps of bright regions, which is noise, likely from ground motion. Unfortunately, this is the situation that we have to face. How we deal with it? We can subtract, in some cases, this noise. There are a few techniques described in the paper, the two papers represented referenced at the top. The idea is to correlate the signals from two detectors and identify only the correlated part, or correlate signals from a detector, the strain from a detector, and an auxiliary channel, and remove the correlated part, okay? One important hypothesis is that the auxiliary channel is not able to witness the gravitational wave signal. And this is why we do injection campaign to identify safe channels, safe meaning not witnessing gravitational wave. So these are the conclusion. And I want to conclude with sort of bold claim, that is detector characterization is a set of techniques that helps you to turn imperfect instrument into precision observatories. And I described a few ways in how we do this. I just skip to the last bullet point. So in the previous slide, I made several references to the data quality flags available on GWOSC, either Cat1 flags or the line catalogs. And this allows to make a detector characterization not just an effort of the LIGO Virgo and Kaggle collaboration, but a community effort. You can practically do detector characterization yourself, thanks to the availability of Cat1 flags, spectral line catalogs, and also do comparison of the strain with the glitch and without the glitch, as I was showing in one of the last slides. And this is, okay, you have already seen the last slide. Okay, too late. In the previous slide, I've put some references. So thank you very much for your attention. Oh, wow.
Perfect. Thank you, Francesco. I just want to add something. The GWOSC also releases the auxiliary data channel. A few of them. So you can really help hunting the noise hunting process. Okay. As usual, we have a few questions online. So there is a question by Sampriti Mandal. Why are we using the Fabry-Perot interferometer? I have done the experiment and seen it produces a very stable interference pattern and not quite sensitive to path length. Basically, why are we using the Fabry-Perot interferometer?
Well, so I think okay, they have some experience on optics. The simple reason is that it's a practical way to increase the arm length, which, as I showed in the first equation, is just a simple equation. The effect that we can measure of the transit of our gravitational wave signal is proportional to the arm length of the detector. Using Fabry-Perot resonant cavity just increase it. There could be complication in tuning these cavities, but I think I'm not qualified to answer this part of the question. I mean, it's related to the experiment. I mean, it's a practical way. So probably one can refer to, well, from some notes by Rainer Weiss of the early 70s to various later documents describe how effective Fabry-Perot cavities are in achieving this. It's kind of even more stricter improvement to the basic Michelson interferometer layout than adding signal recycling or squeezing. So we have been using Fabry-Perot cavities since the beginning. It was effective.
Also, I think, as you said, this person has a some experience with optics, but in those detectors, we have to push the precision by a lot, many order of magnitude. So yeah, basically you pushed, well, LIGO, Virgo, and Kagra pushed the limits of what was previously done in optics.
Yeah, yes.
Thank you. There is another question by Claire Riguzzo. Can you elaborate on what causes the coating Brownian noise? Very specific.
So it's a noise from thermal agitation of the atoms, of the molecules of the coating. The coating is the thin layer that makes light to reflect. So this is probably the clearest reference is the fluctuation dissipation theorem, which relates the temperature of an object to its displacement. And if the molecules of this coating moves, then you cannot precisely locate where is the reflecting surface. And this is the origin of that noise. Yeah, I think that, I don't know if this is sufficient. Of course, one corollary of what I just said is that it will be beneficial to have cryogenic test masses. And this is what the Kagra detector is trying to do. So they bring their test masses to like 30 Kelvin or so, trying to reduce this kind of noise. But in doing this, you need some big coolers, which introduce some other kind of noise. So it's always a sort of trade-off. You want more vibration noise for the refrigerating apparatus, or you want less Brownian noise. So it's always a trade-off. For the moment, the second G detectors have not implemented that. Kaga, which is a 2.5G detector, has tried to implement that. Next generation detector, Einstein Telescope, Cosmic Explorer, are likely to implement that, but it's difficult.
So there will be a talk on next generation detectors.
Right, by John.
Oh, you did that. Also, I think LISA is based on a totally different
yes,
detection mechanism. Okay. There is one last question online by someone named Krish. What are the limiting factors in adding more mirror or cavities?
Oh, that's a good question. Like a more complex layout than this. So basically, there has been some Einstein telescope optical layout called like the xylophone layout or etc., which involves many more mirrors. I can comment as people close to the detector and doing detector characterization. So it's already a huge mess to characterize 4 test masses and these 5, 6, 7 mirrors. So introducing more will be hell complicated. So as I showed in one of the slides after this one, even in this simple scenario, we don't understand like 10% of our sensitivity or sensitivity deficit. So with more mirrors, we risk to understand even less. So for the moment, we are good with this. Let's try to push this configuration to the limit and then maybe see if we can add something more.
Any question here in the amphitheater? Don't forget, it's the time of the coffee break. So we have to.
You can chase me at the
very
coffee
quick
break. I mean, if you wish. Oh, I forgot to get my tag.
I just had a question. So if I understand correctly, you talk about vetoing and specifically frequencies, and the plot looks very red. So
very red, yes.
I suppose the question is, when you say veto a frequency, do you just get rid of it completely? And if so, what happens to your analysis? I mean, you would lose real data in vetoing these frequencies.
So first of all, which kind of search are you doing? Probably CBC search can ignore most of these frequencies. Probably only the louder frequencies are notched, but the rest gets passed through. And in this catalog, indeed, we give the amplitude of the lines. Here is very red because I literally included everything. So they are a few hundred of lines, which in a tiny plot gets really squeezed. So it's really red. But if we go back to here, these are like 40 hertz of frequency in this plot, from 30 to 85, like, and there are, okay, probably 20 lines, but they are really, really small. So the amount of vetoed region in a CBC in a CW search, a continuous wave search, is quite small. Okay, so there are many frequency beams in high resolution analysis, and a fraction of them is vetoed. So we are talking about less than 1%. Of course, if you're doing targeted searches, so like Villa Purser, you are really interested at 60 hertz, you can ignore everything that's happening around. So you look at around 60 hertz, okay, it's clean in Virgo data, good. Unfortunately, it's not clean in Hanford or Livingston data because the mains in the United States is 60 hertz. Or, well, for Pulsar between 45 and 52 in Virgo will have problems. So this is more or less the logic.
Well, thank you again.
Thank you.
I think it's time for a well-deserved coffee break. And we will convene at 4 for the last talk of the afternoon. Thank you. And for people online, you have a few minutes to enjoy your break too.